How come the sky is blue? And how is a rainbow created? We get up, wash ourselves, eat a small breakfast, and then drive to work every day of our lives. A gorgeous blue sky on a sunny day will inspire us to start working right away. Conversely, if it's raining but the sun is still out, we may be able to see a spectacular rainbow that will make us happy and amused. After spending the entire day at work, we eventually get home and, if it's a special occasion, we might enjoy a romantic aperitif with our special someone in one of those locations with a breathtaking view of the city. After a long day, we'll take a break and enjoy the beautiful sunset. Some of us might prefer to leave the house after supper and climb a hill outside of the city to spend a romantic evening gazing up at the stars with their significant other. But do we ever ponder why the sky changes from blue to crimson to dark at night throughout the course of the day? And why a rainbow forms only if it's raining? Follow me in this video for a terrific tour through some common but fascinating entertaining facts about optics if you want to learn more about this. We need to take a step back and attempt to provide an explanation for a fundamental question before moving on to the explanation of these common phenomena. What is light? The primary field of study for this subject is optics, which Isaac Newton pioneered in the 17th century. Everyone at the time believed that light was a wave with its own wavelength, the space between two subsequent peaks, frequency, and intensity, the height of the peaks. Two important aspects of light behavior were investigated during that time: reflection and refraction. The first occurs when a ray strikes a reflecting surface, such as a mirror, which prevents any light from passing through and reflects the ray at the same angle of incidence. The second occurrence is typical of non-completely reflecting surfaces. When light travels through one substance and then another, its trajectory deviates. The divergence is inversely proportional to the disparity in densities between the two regions. Have you ever seen what happens if you point a laser on a glass of water? When the beam penetrates the fluid, it bends in a different direction. Physics researchers later established that light is just a sort of electromagnetic radiation with a certain range of wavelengths that are visible to human eyes, between 300 to 700 nanometers. This discovery was made in the 19th century with the help of the renowned James Clerk Maxwell. In actuality, the wavelength of light is the only physical distinction between it and an X-ray, gamma ray, or infrared. These radiation types experience the same reflection and refraction effects. For instance, the sun's rays seem white because they include an equal amount of each visible wavelength, whereas sodium-fueled special lamps emit an orange light because their emission is primarily made up of certain sorts of wavelengths around 600 nanometers. Also, in the final 50 years of the 19th century, scientists were able to more firmly describe a larger variety of luminous phenomena thanks to the development of sophisticated mathematical techniques. They were aware that the wavelength of light affects the angle of refraction. This allowed scientists to explain some effects that had been noted by earlier physicists like Newton. Do you know what Pink Floyd's iconic logo is? It's one of their more well-known symbols. A prism. And why is it important? The prism has the capacity to distinguish between several light ray wavelengths. How does it accomplish that? The beam directed towards the prism experiences a first refraction when it enters the glass and a second one as it exits the glass and returns to the atmosphere. The components of the original light are divided into what we refer to as the spectrum as a result of this double refraction, which causes all the various colors to travel in space in slightly different ways. Did you know that the wonderful rainbows you see after a rainy afternoon are caused by a similar phenomenon? Do you have an explanation for those events? We need to ask ourselves this in order to find a solution to this issue. What are the two major requirements for the appearance of a rainbow? It is rain and sun. And as a matter of fact, the solution is already contained in those two words. Let's begin with the first. What is rain made of? Water. And how do we depict rainwater in a sketch? It can be visualized as a group of spheres of various sizes. We can now focus on the second characteristic of a rainbow's formation, sunlight. As a beam of sun rays reaches a sphere of water, it suffers a first refraction, a second reflection on the rear of the droplet, and a final refraction when coming out. This procedure causes light to be dispersed, much like in a prism. The rays will emanate in a variety of directions since the droplets are positioned differently. Thus, when we consider rain as composed by a great amount of water droplets, the final impact is the separation of sunlight in its many colors, the rainbow. In addition, another distinct substance allows for the observation of a comparable effect. Have you ever noticed something odd at a gas station while you were filling up your car? Due to the same dispersion, when some oil spots are exposed to sunlight, they create a small rainbow. We need to define a new phenomenon called scattering before we can continue with other commonplace interesting facts. Scientists learned at the beginning of the 20th century that light was quantized into tiny particles called photons. Suddenly, they began to have second thoughts regarding light's appearance as waves and moved closer to a more corpuscular description. Thus, physicists discovered that each particle has an undulating behavior with the invention of quantum mechanics, a model that can better describe particles than any other theory. As a conclusion, we might argue that depending on the circumstances, light can be regarded as either a particle or a wave. This idea allowed researchers to explain how individual atoms interact with radiation. This specific phenomena is also referred to as scattering. The results of the interaction rely on how big the atom is in comparison to how the wave behaves. The atom quickly absorbs light and re-irradiates it, producing fresh photons. First off, Rayleigh scattering, named for the 19th century British scientist Lord Rayleigh, is used when a particle is significantly smaller than the wavelength of the radiation. It is feasible to discover that the power of light diffusion is inversely proportional to lambda 4. Due to this, blue, which has a shorter wavelength of 500 to 520 nanometers, is heavily reflected compared to red, which has a greater wavelength of 700 nanometers. Our sky is blue because of Rayleigh scattering, which describes how the particles in our atmosphere interact. Your response may have been satisfied by this demonstration, but an accurate spectator won't be completely satisfied with these claims and will still be skeptical. In actuality, a single query seems to undermine this claim. Do you realize it? Why is the sunset red? Air always functions in the same way and according to Rayleigh rules, but blue is completely absent. Why is it the case? The solution is rather straightforward. A thicker layer of atmosphere must be penetrated by the sun's light as it sets at the end of the day than when it rises in the morning. While blue and green components are emitted with a higher power, they are consumed after a given distance traveled in air, and only the other hues like red, purple, and orange remain visible. Continuing forward with this issue, other questions might surface about the sky. For instance, why is the sky dark at night? What happened to our atmosphere? When the sun is not illuminating it, the atmosphere is transparent. I'll attempt to give you an understandable example. Have you ever driven with fog? What occurs when you turn on your headlights? Light interacts with the water vapor in the fog and experiences some scattering. Our vision is much more obscured by the fog and the dispersed rays. On the other hand, the fog appears to be less dense when we dim our headlights. On Earth, the same thing occurs at night. When the sun sets, the atmosphere loses its illumination and almost completely transparent, allowing one to see stars and the dark background of space. Suntan is the final but not the least impact that will make you feel completely stunned. Have you ever wanted a gorgeous tan in the summer heat? Well, this phenomenon is underpinned by a lot of optics. Let's examine it. Previously, we stated that solar light is white because it contains all hues equally. As a result, the sun emits more than just electromagnetic visible radiation. In reality, it emits radiation at other wavelengths, such infrared. Visible light has beneficial benefits on our bodies, but other frequencies of radiation that are damaging to our organisms cannot be compared. Some of the harmful rays may reach the ground even though the majority of them are completely absorbed by our atmosphere, which serves as a shield and supports life on Earth. In particular, UV rays are well known. They have the potential to severely burn our flesh. Thankfully, melanin, which is found in our bodies, provides excellent protection against sunshine. It is a naturally occurring pigment that has a limited capacity to absorb UV rays and can appear in two different colors, red, pheomelanin, and brown, eumelanin. The organism begins to produce melanin at a higher rate when the sun touches our skin, lowering the chance of getting a sunburn. But how does melanin manage to give us that lovely tan we adore flaunting at the beach? There are two basic processes. The first is melanin oxidation, which causes the pigment to become darker and darker. Even if we are completely tanned in this situation, we should continue wear sunscreen because we have no additional protection from future UV rays. On the other side, there is an alternative method of tanning. Our bodies produce an excessive amount of melanin when UVB photons predominate because delayed tanning is much more protective than oxidative tanning. A skin tan, thanks to this procedure, may be able to sustain UV radiation 3 times better than a regular one. In conclusion, there are many phenomena around us that, despite seeming commonplace and unremarkable, actually conceal a variety of astounding physics consequences. Most people have probably never given much attention to the genesis of a rainbow or a breathtaking sunset, but science is there to try to find a probable explanation for these occurrences, and it never ceases to amaze and astound people. Alright, everyone, here's where the video ends. Thanks for viewing, everyone. Are you intrigued by this subject? Are you astounded by the explanation of these amusing real-world facts? Please share your thoughts in the comments section below. Don't forget to subscribe, and I'll see you on the channel again soon.